This is video 90 in our series on tensor calculus. In this video, we'll pick up where we left off in video 88 and complete our review of surface analysis as it applies to curves. We spent the entire last video analyzing the vector curvature normal. We said that this new object is equal to the Laplacian of the position vector. We also showed that it can be represented in several alternate forms. First of all, this one, which gives us a convenient way of evaluating this new object using curve coordinates. We then went on to show that it's also equal to the second derivative of our position vector, which means it's equal to the product of the curvature and the principal normal, both of which we defined back in video number 76. Well, this in turn tells us that our vector curvature normal can be expressed in this form, which is simply the product of the magnitude of this vector times the principal normal. In this form, it's very clear that the magnitude of our vector curvature normal is simply the curvature of the line. Now, this new form reminds us of something that we ran across during surface analysis, namely B alpha alpha times n hat. Now you'll remember back there that B alpha alpha is a contraction of our curvature tensor, and we called that the mean curvature. We showed that it's also equal to the sum of the principal curvatures of the surface. So looked at in that light, these two things are completely analogous to each other. Here we have what is effectively a mean curvature involving only one principal curvature. Well, in both cases, these terms represent a projection away from the manifold. Here we're projecting onto a normal. Here we're projecting onto a surface that is perpendicular to our curve. Therefore, what we can say is that any surface relationship that involves this term will apply equally well to curves if we simply replace it with this term. So with that in mind, let's pick up where we left off in video 88 and complete our analysis of surface relationships as they apply to curves. We'll start with the Christoffel symbol. Here everything works exactly like it does for surfaces, including the explicit definition, transformation, objects of the first and second kind, and the explicit formulas for the object. Now, note for a curve, since all of the indexes have to be a value of 1, then there's only going to be one Christoffel symbol for the curve. That simplifies things greatly. For example, these two terms are equal, therefore we can add them together and have 2 of this factor. Here, these two cancel out, these two cancel out, and these explicit forms resolve to this. In particular, notice this one, how simple it is to find the one and only Christoffel symbol. It's just 1/2 of the derivative of the covariant metric tensor with respect to our coordinate. And then, of course, to find the Christoffel symbol of the second kind, we simply raise the index by multiplying by this factor. The conversion formulas for the Christoffel symbol work just fine for a curve and are completely self-explanatory. The covariant derivative is defined for a curve just like it is for a surface. It takes on exactly the same forms for each of these definitions. Notice, however, that these first two forms are limited to vectors that lie on the manifold. Well, for a surface, that means that these vector components have to relate to a vector that lies on the tangent plane. For a curve, that means that these vector components have to relate to a vector that lies tangent to the curve. Other than that, everything is the same. And we can extend these definitions for higher ranks like this, and we can also apply the chain rule. So there's really nothing new to add about the covariant derivative than what we've said in past videos. Here we have the formula for the partial derivative of vectors that lie tangent to the curve. When we perform this operation, we're going to get a projection onto the curve and a projection away from the curve. This is similar to what happens for a surface. We start with a vector that lies in the tangent plane. We'll get a surface projection and a normal projection. Notice that this is a great example of the fact that for a curve we're using p hat and not n hat. P hat is analogous to our normal for surfaces. Next we'll look at the metronomic property, and here the results turn out to be exactly the same as they were for a surface. We find that all of our metric objects are metronomic except for our basis vectors. So the covariant derivative of either the covariant or the contravariant basis vectors are not equal to 0, but they're equal to these factors. Now notice again for a curve that we're using p hat and not n hat. It's the principal normal that we use instead of the surface normal. The definition for the contravariant derivative is quite self-evident and requires no further explanation. The definition for the Laplacian is very straightforward. However, there is an important point to make about curves. For a curve, if the object here is an invariant object, then the Laplacian will always resolve to this form. It's the equivalent of the second derivative of that object with respect to the arc length of the curve. Now you'll remember we took advantage of this property when we were analyzing the vector curvature normal. But the point here is that this is a property that is true for any invariant object, not just the position vector. Finally, we'll look at the Riemann-Christoffel tensor. Now these definitions are certainly valid for a curve the same way they are for a surface, but for a curve something very interesting happens. First of all, notice that if all of these indexes are equal to 1, then that means that the Riemann-Christoffel tensor has only one component. And if we look at these terms, again, if all the indexes are 1, then these two terms are the same, so they'll cancel. These two terms are the same, they'll cancel. Same thing happens here. And what that means is that for a curve, the one and only component of the Riemann-Christoffel tensor is equal to 0. That in turn means that all curves are intrinsically flat. There's no such thing as intrinsic curvature for a curve. So there's no analogy to Gaussian curvature when we're looking at curve manifolds. Now when you think about it from a geometric perspective, this makes perfect sense. We can always parameterize a curve simply with its arc length. And if you take such a curve and straighten it out into a straight line without stretching it, then we have a simple number line. So all curves are isometric. Anyone who's simply taking measurements along the curve will see it as a Euclidean space, and they won't have any sense or any measurement of any kind of intrinsic curvature. All right, with all of that, I think I've made the point that we've been trying to make for the last 3 videos. And that is that to analyze a curve, all we need to do is to make application of the surface relationships we derived earlier, making sure in each case to limit the values of the Greek indexes to 1, and making sure that we replace the surface normal n hat with the principal normal p hat. As long as we do that, we don't have any additional work to do when it comes to analyzing a curve. So to pull all this together, I want to spend the rest of the video showing you how this works for a specific example. As a sample curve, we're going to look at a spiral. The first thing we need to do is to assign a value for our parameter, and we'll use the value of t, which we'll equate to our curve coordinate u1. The ambient coordinates are simply our Cartesian coordinates of x, y, and z. So the next thing is to come up with the parametric equations. We need to find out the relationship between our coordinate t and the ambient coordinates x, y, and z. For a spiral, these relationships will work very nicely. Here a is a constant, so what I've got is the values of x, y, and z each expressed of functions of the single variable t. The next thing we need is the shift tensor, and we get that according to this formula. It's simply the derivative of each of our functions here with respect to our curve coordinate t. So that result is going to look like this. I'll let you validate that on your own. These values here are simply the derivatives of each of these respectively with respect to t. Notice that for a curve, our shift tensor consists of 3 rows and only 1 column. Next, we can use this relationship to derive our covariant basis vector. This is just a linear combination using each of these 3 components of our shift tensor in conjunction with the basis vectors in the ambient coordinate system. So it's going to look like this. Each of these vector components are just the components of our shift tensor right up here. Note that for a curve, there's only one covariant basis vector. Next is the covariant metric tensor, and for that we use this expression. And for a curve, since all of these indexes have to be 1, there's only one possible combination. So the one and only component of our covariant metric tensor is simply the dot product of this covariant basis vector with itself. And when we do that, you square this term, square this term, square this term, add them all together, and you get the only term, which is this. I'll let you validate that algebra on your own. Next is the volume element. The volume element is just the square root of the determinant of our covariant metric tensor. And in the case where there's only one component in the matrix, then that one component is also equal to the determinant. So all we've got to do is take the square root of this individual term. That gives us this for the volume element. Now for a curve, we said the volume element is also the value of the magnitude of our covariant basis vector. So that gives us this value up here. Now in other cases, we would have gone down the diagonal elements of our covariant metric tensor, and taking the square root of each one gives us the magnitude of our basis vectors. Well, in this case, that works too, because this is the only diagonal element, so the square root of this is equal to that. So it works either way. We define the contravariant metric tensor using this expression. And in the case of a curve, it's very simple. These are both individual terms. We just need to find the reciprocal of this individual term here. And that's easy. We just invert it like this. So these two are simply numerical reciprocals of each other. Multiply them together, we get the value of 1. For the contravariant basis vector, we use this expression. This tells us that we just need to multiply the contravariant metric tensor times the covariant basis vector. That's this term multiplied by this basis vector. And when we do, this is the result we'll get. This is the contravariant basis vector. And of course, for a curve, there's only one. For the magnitude of our contravariant basis vectors, we find the square root of our diagonal elements of the contravariant metric tensor. Well, of course, in this case, that simply means the magnitude is the square root of this one element. To find the inverse shift tensor, we'll refer to this expression and just reverse engineer it. If our contravariant basis vector is equal to this linear combination, then these factors must be the vector components of each of these terms. That means our inverse shift tensor is made up of these components. Notice that for a curve, there's only one row and 3 columns. For a curve, we said that our metric equation is going to look like this. So it's a simple matter to substitute in the value for the volume element here, and we get this expression for the metric equation, and that of course leads immediately to the expression for the arc length. We showed that for a curve, finding the Christoffel symbol is really pretty easy. We said to find the Christoffel symbol of the first kind, we'd use this expression. It's just 1/2 of the derivative of the covariant metric tensor with respect to our coordinate. So in this case, that's going to look like this. And then to find the Christoffel symbol of the second kind, we just need to raise this first index. So we use this expression, we multiply this by the contravariant metric tensor, and that's going to give us this result. Next, let's derive an expression for the unit tangent vector. And that's pretty easy. We just need to divide the covariant basis vector by its own magnitude. Remember that the magnitude of our covariant basis vector is just the volume element. So what I've done here is I've divided the covariant basis vector by the volume element. And there's a factor of a in both of these that is canceled out. So this is the result giving us the unit tangent vector s hat. Well, let's move on and see if we can find the vector curvature normal. Well, to do that, we first have to find the derivative of this expression with respect to t. And that's a lot of work. It's pretty tedious, but if you go through the exercise, you'll find out that it looks like this. This is the derivative of s hat with respect to t. Well, that's not quite the vector curvature normal. To get that, we have to include another factor of 1 over the square root of u. You'll remember from our earlier discussion that this is an alternate expression for the vector curvature normal. So when we take this expression and multiply the denominator by the volume element, we add a factor of a times the square root of 2 plus t squared, which increases this exponent to 2. So what we have here is the expression for the vector curvature normal. Okay, to complete the exercise, we need to find the curvature and the principal normal. Well, the curvature is just going to be the magnitude of the vector curvature normal. So to find that, we need to find the dot product first of all. And to find the dot product, we're going to have to square this term, square this term, square this term, add all that together and divide by the square of this term. And if you do all of that, and then take the square root of it, you're going to find the magnitude of our vector curvature normal. And that's going to be this. And of course, the magnitude of our vector curvature normal is also the curvature of the line. Okay then, finally the principal normal is just going to be this vector curvature normal divided by its own magnitude here. In other words, we just need to divide this expression by this one. And in the process, these two factors will cancel out, and the result we're looking for is going to be this. So this is the principal normal. It's a unit vector that points in the same direction as our vector curvature normal. All right, I went through all that pretty quickly, so I strongly recommend that you go back and review it at your own pace. You may not feel the need to perform all of the calculations, especially the more complex ones that are on this page, but at least make sure you understand the process. Now to tie all this together, I want to end the video with a short demo. Here we have our spiral, and there's a point on the spiral that we can move along the curve like this. The first thing that I'll do is to display the coordinates. And our coordinates for the spiral are going to be this value of t, that's our parameter that we've been working with all along. I've also got the Euclidean distance s. This is the distance from the origin of the curve here all the way up to the point. And of course you can plainly see they're not the same. I've also got the x, y, and z coordinates for the Euclidean ambient space in which this curve is embedded. Well, let me move the point along the curve, and you can see how t and s change. Not only are they not equal, but they're not changing at the same rate. When we get down to this point, s is actually less than t. We move up, it becomes larger than t. So the thing that relates the rate of these two values is our line element. So I'll display that here. This is the rate at which one of these is changing with respect to the other. So I guess the next thing to do is to look at the covariant basis vector. Let's put that up right here. And you can see that it is tangent to the curve, and it is not unit length. In fact, to see this better, let's tip it over on its side like this. If we look down from the top and we move the point, you can see that the length of our covariant basis vector changes depending on where we are on the curve. You'll remember from the analysis that the length of this covariant basis vector is actually the line element here. So right now the length of this vector is about 2 units. To kind of drive that point home, let me put up the unit tangent vector. That's the vector in green here. This is a vector that's tangent, but it has a length of 1. So as we move along the curve, you'll see the value of the covariant basis vector increase because the value of our line element is increasing. Move back to a point like right here, and they're almost equal, and now the covariant basis vector is shorter than the unit vector. Okay, so let me then add the contravariant basis vector, and that'll be this shorter vector right here. So as we move along the curve, one of them gets longer, the other gets shorter. Their lengths are reciprocals of each other. Okay, let me take the covariant basis vector off and the contravariant vector off. So we're left just with our unit tangent vector. The next thing is to look at the principal normal. So that's a vector that points in the direction of the curvature. So it's going to be perpendicular to our unit tangent vector. It's perpendicular to s hat at all points, and it also points in the direction of the curvature and lies in the plane of the curvature. So let me display the curvature plane here. The two vectors I have here, p hat and s hat, will define this plane, which is the plane in which the curvature is occurring. Let me just put this in motion, and you can see as it moves along the curve, the plane corkscrews its way up the spiral in order to continue to be in the plane of the curvature right here. So the principal normal then is associated with our curvature, so I can put up that value as well. This is the numerical value of the curvature as it's changing along the curve. Notice near the origin, the curvature is greater than it is as it moves out. As it extends outward, the spiral is sweeping in larger and larger sweeps, and therefore the curvature is getting less and less as it moves into bigger and bigger circles here. All right, with that, I think you have a pretty decent visual understanding of what we've been working with. So we'll bring the video to a close. In the next video, we're going to introduce one more topic relative to curves, and that is the Frenet formulas.